Okay, here we are back. We're using this summation notation or summation formula for a geometric series. And here's the first one we're going to apply this to. So we have a summation as I goes from 1 to 12 of this expression, 4 times 0.3 raised to the I minus 1. So let's generate a few of these terms so we can convince ourselves that it actually is a geometric series. So when we put I equals 1, this becomes 1 minus 1. So 0.3 to the 0 is just 1, like anything raised to the 0, times 4. So the first, when I equals 1, it generates a 4, plus then I equals 2. There we have 4 times 0.3 to the 1. And when I equals 2, it's going to be, when I equals 2, 4 times 0.3 to the 2, and it's going to continue that way until we get to 4 times 0.3 to, when we put in that last term, notice when we put in a 12 here, we get I, or 12 minus 1. So the last term is going to have an exponent of 11 there. So we can see that whole thing. Now that definitely is geometric, and it's of this, it must be in this form, this A times R to the I minus 1 in order to use this formula. And it is. So we check that. Check, check, check. Alright. So let's actually use it now. The sum of these 12, sum of n, or 12 in this case, the sum of these 12 terms is a sub 1, which is the first term we generated was a 4, times 1 minus the common ratio. What did I multiply each term to get the next? Common ratio, 0.3, raised to the n, our n is 12, over 1 minus 0.3. Alright, so when you tippy tap that out in your calculator, you'll see it comes out to 5.714. Alright, so not so bad of a formula, and certainly works quicker than adding up those 12 terms. Alright, just a word of caution. I'll show you another problem that's very close to this, but we can't use this without some adjustment. So say we have something similar. I equals 1 to 12 of 4 times 0.3 to the I. Ooh, so it looks really close, but you can see right away this is a little different right there. So let's generate a couple terms, see what it looks like. We have I equals 1, so we get 4 times 0.3, and then we have the rest that follows. 4.3 squared, 4 times 0.3 cubed, and so on. And when I do that, this is term 1, 2, 3, so we'll go on to 4 times 0.3 to the 12. Alright, so when I do that, I see the difference from here to in this one, because here in the very first term there was no mention of the common ratio. It was just the first term. Here the common ratio appears, but in this first term the common ratio appears right away. So this is not set up to use this formula. It has to follow this form. So we can have a little trick up our sleeve. I think this will help. Let me see where my work is. If I pull out a 4 times 0.3 out of every one of these terms, what do I have left? So I'm factoring it out. So what do I get when I factor out? That means divide out a 4.3 by a 4.3. 4 times 0.3, I'm sorry, you get 1. Here the 4 will be pulled out, but the 0.3 will leave 1.3 there. 1 factor of 0.3, and then we'll have one of these removed, so it'll be squared and so on. And the very last term will be 0.3. Let's see, this one gave us 1, this one gave us 2, so this one should give us 11. Okay, it will. Alright, so let's see. There's still 12 terms, but that last one, exponent, will be 11. So now this does follow a pattern where we have the first term, then the second term is the common ratio appears once, twice, third, fourth term 3 times. So this one does follow. So the 4.3 will be outside of our formula. It won't be used. So now I'm inside of this box. So I'm going to actually start doing this, and then at the end I'll multiply whatever this box yields by 4 times 0.3. So this is sort of on hold. Alright, so what was our first term when we did that? The first term was a 1 in this bracket, and then parentheses 1 minus our common ratio was 0.3. There were still 12 terms in that box, so we'll still use a 12 over 1 minus 0.3. So when I get that number, I'm going to multiply it by 4 times 0.3. So do you see that adjustment I had to mess with? When I tippy-tapped all that out, I got 1.714. Alright, so you can, it's one of those things you probably will get it better after you do a couple yourself. But that time is not now. So write that down so you kind of refer to it when we run up against it in class. We'll finish with a discussion on this summation. Suppose we go, let's say we have, I won't write it in summation notation, we start with 2. And we're going to add a half, and then a fourth, and then an eighth, and a 16th, and so on. So is that a geometric series? Notice I'm not stopping anywhere. These dots means it goes on forever and ever. So we are summing from the first term, say I equals 1, to infinity. So is it possible to add up an infinite number of numbers is my question. Well, the answer is sometimes it is possible and sometimes it isn't. This one that I show you is possible. Let's see what happens in our box if we go infinite. Because the sum of n numbers, which is now going to be infinity, is a sub 1 times, I'm just filling in our old formula from up here, that same one, 1 minus r to the n over 1 minus r. So what is r in this example? R is 1/2. So if I replace the r's with 1/2 for this example, and how many numbers, how many terms, our n is going to go on for infinity. So what happens to this number? What is 1/2 to the infinity? So let's start with that. You can kind of see where it is by looking at, say, at 1/2 to the 10 and then 1/2 to the 100. And when you do that, this is like 0.00009, I think 77. So 0.0000977. But 1/2 to 100 has 0.00030 times and then a 7. So you can see that in infinity 1/2 raised to infinity is actually 0 exactly. So we can drop that, it zeroes out, and look what's left. We have a sub 1 over 1 minus r, which in this case is 1/2. So this is going to be the formula, but in this case we get a sub 1. What was our first term? A 2. So we're going to get 2 over 1 minus 1/2, or 2 over 1/2. And when we do that, it gives us, you know what? I didn't do that right. I'm sorry. I'm sure you picked that up, but I should have started with a 1 because I did 1/2 times each one. I could have started with a 2, but then I'd have to erase all of them. So if I change that to a 1, it's perfect. So 1/2 times 1 is 1/2 times 1/2. So when I get over here, I'm going to have a 1 up here. The first term should have been a 1 to make it a true geometric series. Sorry about that. So 1 minus 1/2 is, 1 divided by 1/2 is 1 times 2, or 2. I think that's where I got the 2 from. All right, interesting that I can add up an infinite number of numbers and get an answer. That's shocking to me. That is, if you add up all of these and you continue in this pattern forever, it will equal exactly 2. So, chew on that one. All right, I will mention that this formula doesn't work, because look at this, a sub 1 times 1 minus r to the n over 1 minus r. It only works for certain r's, because that's why I said sometimes we can do it and sometimes we can't. So suppose the expression was 2 plus 4 plus 8 plus 16 plus 32. Here, the common ratio, what did I multiply each term to get the next? The common ratio is 2. So if I go into this formula and put a 2 there, I get 2 to the infinity. If I'm going to add up if I'm not stopping anywhere, I'm going for infinity. 2 to the infinity just gets bigger and bigger without bound. It does not zero out like 1/2 did. So 2 to the infinity, it just keeps getting larger and larger without bound. So we say then that this one we cannot do. This diverges. The 2 to the infinity will keep going and going. This 1/2 to the infinity became 0. So to summarize that, here's how it works. R has to be between -1 and 1 in order to find the infinite sum. And it's going to be a over 1 minus r, which is a lot simpler than our finite sum, which is this up here in the box. That's not too bad, but look how simple this one is. All right, so this is our formula for an infinite geometric series sum if r is between -1 and 1. So it's going to be a fraction between -1 and 1, like -9/10 or +3/4. Any fraction within that band will yield an answer, and this will be it. Any common ratio outside of this band will not have an answer. All right. That's all for this weekend. I hope that your weekend is full, relaxing, and I will see you on Monday. Till then, over and out.